Hi guys, I would like to welcome you on this lesson 2 of Advanced PCB Layout course. Today we are going to speak about how to set up basic stack-up and basic rules, how to do fan-out in the processor area, especially for the decoupling capacitors, for the memory interface, how to do fan-out for the memory chips, and how to connect the memory chips and the processor together. Let's have some fun out today. Before we will start doing any layout, we will set up a basic stack-up. Right-click, Options, Layer Stack Manager. At this stage, it's only 2-layer PCB. That's not enough for the design like the module. We need to add more layers. So add layer, add plane. Do you know what's different between layer and plane? Plane is full of copper connected to one net. Signal layer, this layer is the standard layer where you can draw tracks, you can draw their polygons. How many layers we need to add at this stage? Doesn't matter. Just add as many as you think you will need, and if it's not enough, you can add layers later. If you don't need all of them, you can delete the layers later, no problem. And I will name them with something simple and short, so it's very easy to see here on the bottom. It's very easy to switch between them on the bottom. It's very easy to use them in rules, in filters. We use just L1, L2, L3. It's clear and it's useful name. In the next lessons, we will speak about how to decide exactly on the number of layers and how to order the layers, because it's very important how you order the layers. And there are some other parameters here which we will set today. For example, this pullback. Do you know what's the pullback for? It says how deep the copper will be from the PCB edge. In this case, the copper will be 0.5 millimeter from PCB edge. I will change it to 0.1 to 0.1. How these layers are going to be used in our design? This is top and bottom layer. That's clear. This one just below the components, the second layer below the components, and here will be ground. But because we are using microvias, there will be some short tracks and microvias. That's why I use the signal layer. I didn't use the plane. So here will be some small tracks. This L3 will be the main layer for the tracks. This one, L10, will be main layer for tracks. And these 4 layers in the middle will be used mostly for powers. I also pull back the power planes, from the PCB edge. I pull them back deeper into PCB based on this 20H rule, which says something like this. If the power plane edge is retracted 20H of the ground plane edge, see, power plane is deeper than the ground plane, 70% of the energy radiation can be repressed. So it lowers the radiation from the PCB. I'll show you on the module how it looks. Here is the module PCB. Here is ground plane, 0.1 millimeter from the PCB edge. And here is a power plane. See, another power plane. And if we measure how deep it is from the ground edge, like 1 millimeter. It's not 20 H. H is the distance between ground plane and power plane, but we always do it as deep as possible. And I never seen problems with this kind of PCB, so I use it every time. Even there are some articles, there are some posts on the internet which says this 20H rule doesn't work, or it make even PCB worse. As I said, I never seen the issues, so I continue using this rule in my PCBs. Our stack up is almost ready. Everything what we need to set up now are drill pairs. Right click, options, layer stack manager, and here, down here, drill pairs. Can you see it? Drill pairs specify what kind of drilling will be used on the PCB. All the PCBs usually have standard through-hole via, which drills from the top to the bottom layer. That's this drill pair from the layer 1 to layer 12. On the module, we will have also micro vias and buried vias. So we need to add drill pairs from layer 1 to layer 2. This is one kind of micro via which we are going to use. We will have also micro via from layer 2 to layer 3. We will use buried vias from layer 3 to layer 10, and micro vias on the bottom, layer 10, 11 to 12. Okay, these are all the kind of drillings which we are going to use. If you have created a special layer in your footprint library, for example, a special layer for assembly drawing, what you may want to do is also set something what is called layer pairs. Go here on this color, click, and click on this button, layer pairs. Here you can see we have one layer pair, assembly top and assembly bottom. If you want to add more, you can just click add and choose 2 mechanical layers. Basically what will happen then, this one special layer in the footprint library is split between these 2 layers which are specified here. And for example, for all components which are placed on the top of your PCB, they will use this assembly top layer, and all the components which are placed on the bottom of your PCB will be using this assembly bottom layer. So one layer is split between these 2 layers based on where the component is placed. Now the rules. What are the 2 most basic rules which you need to set up for every PCB? Minimum clearance, that's the minimum space between 2 tracks, and minimum width, that's the minimum track width which can be used on your PCB. For the baseboard is kind of a cheap PCB, and this kind of PCB will be manufactured by someone, by a company which doesn't have very advanced PCB manufacturing technology. So you need to always ask them or check with them what are the limits, what are the minimum values which you can use on your PCB. Or you can find it on their website. For example, this is the company where we manufactured the baseboard, and they say minimum track and gap size is 0.12 millimeters. A small tip, if you want to convert between millimeters and mils, you can use Google, just write like this, very useful. So 0.12 millimeters, that's 4.7 mils. We didn't use the minimum value. They usually have also some kind of pricing for limiting values. So the limiting values are the most expensive one, and we use 0.15 for the clearance. If we go to our PCB, this is the baseboard, design, rules, you can see the minimum clearance is 0.15 millimeters. For the minimum width, you remember what was on the website? 0.12. We didn't use 0.12, we didn't use 0.15, we used 0.2 millimeters. Do you know why? It's quite hard question to answer. We didn't speak about impedances, yes, we didn't speak about stack up. It will be in next lessons. At this moment, you just need to know that most of the digital signals need to be routed by 50 or 55 ohm impedance. And on the baseboard, to achieve this value, the best width for the tracks is 0.2 millimeters. That's why we use 0.2 millimeters. The module PCB, that's something completely different. This PCB will be manufactured by a company which has advanced PCB manufacturing technology, and they usually can go as low as 75 micrometers for the minimum track and minimum clearance. That's 3 mils. But I always start routing this kind of design with minimum values such 0.1 millimeter minimum track and 0.1 millimeter minimum clearance. It's 4 mils. And by the end of the design, then I will change all the 0.1 millimeter tracks to be smaller to achieve the 50-55 ohm impedance. At this stage, still too soon speaking about this. Let's set up the basic rules. Go to design, rules. Here is the minimum clearance. So we will set it up to, for the module, 0.1 millimeter. Yes. Minimum width. We will set up 0.1 millimeter. Preferred 0.1 millimeter, maximum 4 millimeters. And press OK. What is also very useful, it's not required, but you may want to set up is minimum track width for all the powers which are in your design for the signals such ground or VCC or this kind of tracks, which needs to be wider than 0.1 millimeter. That's one reason why to do it. Second reason why to set up the different minimum track width for power rails is because, you remember this, by the end of the design we will be changing all the 0.1 millimeter tracks to be smaller. And we really don't want to change any power tracks to be smaller than 0.1 millimeter. I go and open the original design because the rule is quite long, so I can just copy it. Design rules. Here is the rule. Here you specify all the power nets which you would like to have the minimum track width 0.2 millimeters. Right, Control C. OK. I go to our PCB, design rules, width, new rule, double click, name the rule, Control V, and I will add one more net. Do you know which one? Have a look. Which one is missing? I will add ground. Change it to 0.2. Prefer 0.3. Maximum 4 millimeters. And before I press OK, we will adjust one more rule, this one, because vias are the next thing which we are going to do, and we would be getting errors if we don't change this. I know the minimum hole in the via will be 0.1 millimeters, so I will set this to be 0.09, maximum 4 millimeters, and pitch fair will be 0.2. Here I will change it like this. If you need bigger vias in your design or smaller vias, you need to adjust then these parameters. Now I can press OK. Everything what we have to do now is just set up default through hole via, and then we can start the placement under the processor. Go to DXP, Preferences, PCB Editor, Default via, double click. Default via which I used in most of the designs is 0.45 and 0.2 here. Also, by default I mask all the vias. You can do it here like this way, or you can click here to force tenting on the top and on bottom. From layer 1 to layer 12. OK. OK. I go on the bottom layer. I will select all these components here. So this one, move them away of our PCB. And let's do it. I've set up a view for the placement. We can see PCB, we can see schematic, and we are going to apply colors to the power nets which have high number of processor pins connected. This one? No, this one has only one. This one? Yes. We would like to apply color to this power net and also to these other. I know which they are, so I will just select them. I press Ctrl, hold it down, and click on a net to select it. Right click, display override, select on. You may notice that we use plus sign for every power net. For first time I've seen it somewhere in Intel reference design or AMD design, and since then I use it in every design because it's extremely useful, especially during the layout. You immediately see that you are working with a power net. So I highly recommend put plus sign to every power net. Now we can see nicely what paths are connected to power. For the fan out, I always use 0.1 grid, and I would like to see it when I'm doing fan out for the under the BGA. I would like to see the grid. Snap grid, and and just dots. Those are fine. Because now when I'm placing a via, I can see where I should put it. When you are placing vias, always draw the track first and then place via, because then the via will pick up the net name from the track. If you just place a via, it has no name. You would need to assign it manually. We can also check the special rule which we set up for the power net. We can try to change the track width for the ground, for example, to be smaller than 0.2 millimeters. I press Tab and this window will open. I will try to change it to be 0.1. And here you can see trace width 0.1 millimeter is out of range for the current rule. The current rule with power has minimum 0.2. Perfect. Our rule is working for the power nets. So I will set it to 0.4. Do you know why I use 0.4? Under the BGA, when fanning out these power nets, I usually use the track width same as the diameter of the path. So 0.4, that's why I used 0.4 track width. Now we can fan out. Again, press Tab, 0.4. We can fan out more paths. Where do we start? This is quite difficult processor for placement. And it never gets easier. It's always difficult. We will start from the middle. And the first thing what we are going to look for is where the ground pins are located. Why the ground pins? Do you know why ground pins? Because every decoupling capacitor needs to be connected to ground. And when I zoom in, you will start seeing where the decoupling capacitors probably will need to be placed. Can you see it? Here is a power, here is a ground. So the decoupling capacitors probably will need to be somewhere here. Here is a power, here is a ground. Decoupling capacitors probably will need to be somewhere here. Power, ground. Yeah, you are getting the idea. That's what I'm going to do now. I will place here some capacitors, and then we will need to improve it, because they will probably not fit here. They never fit there. You just need to put it there and improve it. Put it there, improve it. Put it there, improve it. On the beginning, it always looks like it's not going to fit. The placement will not look like what you would expect. By the end of the design, it always fits. I highly recommend you to try this placement at home and practice. It's not easy. I'll show you how you can start, how you can do it, and then you can continue by yourself. I will Control C and Control V these main power supplies, so I can see these vias on the bottom, and I can see where is the space for the component, for the decoupling capacitors. Now I would like to see where is this pin. These are connected together, so we need to place two capacitors here. One capacitor here and the other one here. Yeah, this one to this pin, this one to this pin. Here is another net. Here will be this, the coupling capacitor. Okay. Now this one. Okay. This one. I'm doing it because I'll show you. I would like to see if they fit. And even now I can see it will be difficult to fit. See, this capacitor needs to be connected to these pins. And we need to place another decoupling capacitors to these pins. And it's going to be too far from the pin. It's too far. We still need to place something here then later. I'll show you on the bottom side so you can see it. Or I do it this way, you can see it even better. Okay, and we'll try to connect it. It is just to test, to show you what I mean, that it doesn't fit. And I think you can see it now. This resistor, the coupling capacitor, will not fit here. It's too far. What do you suggest? We need to squeeze this somehow. There is one way how you can do it. We can try to place the coupling capacitors this way. See, it needs less space comparing to this space. I will delete all the tracks. I will use this filter. And where we are going to fit them. I'll delete this bias. And we need to find a space, the right space, because we need to fit between these two capacitors. We need to fit a wire. Just press delete. I delete the tracks. Okay. Control C, Control V. Okay, there will be space. And then we can move this somewhere here. And will it fit now? Can move it down a little bit. Perfect. So this was just give you an idea how you can place the decoupling capacitors. We can then move also this. What you need to be careful about? There are some pins in the middle of area. For example, here need to be all decoupling capacitors for all these pins. And in the middle, there is a pin connected to a different net. So somehow you need to fit different decoupling capacitor here. What you need to be careful about also is how far you can go with the decoupling capacitors. For example, what I mean, here the pin starts changing. So here each pin here is different. This means you need to place a via for each of these pins. Means no decoupling capacitors through this line. So the maximum where we can go with decoupling capacitors is here. Luckily, on the other side, there are unconnected nets, unconnected paths. So if you need space, you need to go, or you can go this way, here, and use and place decoupling capacitors here. That's really useful because, for example, for these pins, if we place via here, and we will find what capacitor goes there, this one. We can place it here and we can connect it, and this ground which is here we can very easily connect between these pins. It's very useful if you have some unused pins. Yeah. It's a lot of work, especially when the power rails will be changing, like this area. Here is a different power rail, and here a lot of different decoupling capacitors for this power rail will need to be fit. So all these other decoupling capacitors need to be fit here. You will need to figure out how to fit all the decoupling capacitors there. It's like puzzle or Sudoku. You need to start from something and then do it. Really, really useful. It's sometimes very time consuming, but practice, practice, practice. It will help you. Couple of tips before we move to the memory chip fan out. Always try to place one through hole via per power pin. It's very important. Like this. How do I know these are power pins? Because there is plus in the net name. If not possible, you can connect two power pins to one via. Only in the cases there is no other way to do it. Same for decoupling capacitors. we can connect them like this. Yeah? No, it's better way to connect. What we can improve? We can connect each path to individual via, and we can make this connection shorter. Always try to use as short connection as possible. Now we can move it closer even like this. It's even better. Now we can connect it. Perfect. What would you improve in this connection? We cannot move this yet because we don't know what components will be here. Here probably will be another decoupling capacitors. What we can improve is this via. What do you think? Is better to place this via here? No, place it here. So these two vias are closer to each other. Once you have the placement here, you can try to, for example, rotate this component here and connect it, play with it. As I said before, do something, improve it, do something, improve it. To make it easier when you are browsing through the net, you can, you remember when you click here and select the path, we had to move it. You can go and set the zoom on object. So when I click now, it will zoom in automatically, yeah? Can you see that? Or you can even click on a net. It zooms whole net. And what you also may want to switch off is this net name in the via. It's not really necessary. Click here on this color. Options, do not show. Via net. Okay, it's gone. Yes. Memory chips are designed the way that when you place one memory chip on top layer and one memory chip on bottom layer, the power pins can share same power vias. I'll show you. Here is the top layer and here are some power pins. See? On the bottom layer, same power pins. Don't forget, when you take a chip from top layer and when you place it on the bottom, then the pins are basically mirrored. Very clever people designed this pinout to make our life easier during the layout. I will do the fan out. Oh, wait, shall I place it this way? Or this way? Maybe this way? So many options. Do you prefer a way to place it? What do you think? What could be better way to place it? Or what way could have some advantages to place it? I will explain what I do. When I'm doing fan out for a BGA, I always fan out the first row of the pins out of the BGA, this way, yeah? I don't fan out it inside the BGA. Do it out. There is just little space under BGA, Everything is packed inside, so why to place it under BGA? Go away if you can. And also for this half of the processor, I would place it to the right side, and to this other half I would place it to the left side, this way, yeah, and this way. Again, away from the middle, away from the busiest area. I will just place it here. Now on the bottom we can connect it. It's not always so easy because some of the pins are not exactly on top of each other. For example, here, power, ground, power, ground. When I go on the top, ground, ground, power, power. But again, it's doable. You can connect it, no problem. It is just done a little bit different way. I didn't go with this direction because here will be very busy area. Here will be all the data routed. Go away from the busy area. You can do it by yourself. It's not difficult. This is really simple. Connect all these power pins for the top and for the bottom memory chips. Practice. In reality, you may just do it only once because it is same all the time for every memory chip. These are DDR3 memory chips. So all DDR3 memory chips will have exactly same power fan out. So for all your future designs, you can just copy and paste this fan out. It will save you a lot of time. But it's useful to practice, and it's very important you are aware that the memory chips, the pin out of the memory chips is designed the way that you can place them on top of each other. Let's speak about data signals. In the case you need to use through-hole vias, would you place them closer to each other or further from each other? Closer to each other or further from each other? You need to keep in mind that there will be quite a lot of tracks routed under the memory chip, and you may really want to consider to place the through-hole vias this way, so the gap between them is as big as possible to fit there as many signals and tracks as possible, because this space in the middle will be occupied with some other through-hole vias. You will see. We will speak about this special case next lesson, because this is the case when top memory chip and the bottom memory chip are connected to same data bus. They share same data bus. On the module, we have top memory chip connected to one data bus and the bottom memory chip connected to different data bus. We need to use micro vias. To create a micro via in Altium, it's very simple. Just double click on a through-hole via and specify the start layer L1 and layer L2. Adjust the size. Micro vias are usually smaller than through-hole vias. I know the hole of our micro via is 0.1 and the diameter is 0.27. Be sure it's masked. Ta-da! And we can add more micro vias. We will add a micro via from layer 2 to layer 3. I will just copy, Ctrl C, Ctrl V, double click and change from layer 2 to layer 3. On the bottom, exactly same way. Draw a track, place a through hole via, change it from layer 11 to layer 12, masked 0.1, 0.27, okay, go on layer 11 and copy, Ctrl C, Ctrl V, change from layer 10 to layer 11. It would be very time consuming if you have to do it every time. You can specify this in Altium rules, and Altium will automatically create these micro vias and vias, depends from what layer you are starting and where you are going. I don't use this feature, I normally just copy and paste it. So select, 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 go on the top layer because I would like to have a nice snap point, Ctrl C, I will delete this, Ctrl V, Ctrl V, yeah, easy, quick, no problem. I will clear the errors. To help you to visualize the PCB which we are using, you know, all the micro vias, through hole vias, buried vias, I will show you a nice document which you can find very useful. It's a really good document. Google for Mentor HDI. Click on the first link and go on page 10. This is our PCB. You can see here the micro vias on the top, micro vias on the bottom, through hole via and buried via. There is one very important parameter which you need to consider when you are deciding on the size of your micro vias and through hole vias. Do you know what is it? I'll show you. It's this, called aspect ratio. Read with me. The through via should have an aspect ratio, total length to hole size, less than 10 to maintain reasonable reliability. Do you know what this means? It means that, for example, if in our PCB the through hole via which we use has 0.2 millimeter diameter, then the maximum PCB, maximum thickness PCB which we can use will be 2 millimeters. Yes. If in your application you use thicker PCB, 3 millimeter PCB, the minimum through hole via hole size which you can use will be 0.3 millimeter. And it's even more important for micro vias. I show you. This is the baseboard manufacturer, PCB manufacturer. You can see they specify here drilling, minimum drill diameter 0.2, aspect ratio 1 to 12. But we are more interested about the micro vias. Blind holes, aspect ratio 1 to 1. It's very important. This means the thickness, because we are using 0.1 millimeter micro via hole, the maximum dielectricum thickness which they can drill plus the copper will be 100 micrometers. And if your microvia is deeper, if you need to drill through 200 micrometers, then the microvia hole size need to be 0.2 millimeter. You really need to consider this when you are deciding on the microvia and through hole via size. Here is a picture. Once we went to PCB factory and we took these pictures. This is a PCB cut in half and this is microvia. How it looks, you can very nicely see how it is drilled. So if you need to drill deeper, you need wider hole. And here is a through hole via. Back to the memories, and only what we were not speaking about are these command, control, and address signals. It's not so simple to find out these because we are working with high-speed interface. And the design guide tells you some rules which need to be followed to route these signals. Let's go and have a look. I will Google for IMX6 design guide and I will find the page with the memory interface. It's here. Here they speak about how to route the DDR3 address, command and control signals for our processor. We should use tree topology, balanced T routing. It means from the processor we will go between the chips, then we will split the signal, the track, into two branches. These branches need to be same or very similar in length. And then we will split the branch or segment again, and we will have 4 segments on the end. All these 4 segments, they need to be very similar or same in the length. There are 2 challenges when you will be doing this fan out on the memory chips. The first challenge is that the signals which need to be connected together, they are on opposite side of the memory chips. This part here on top layer need to be connected with this part on the bottom layer. Simplest way to connect them is place a through hole via between them. Second challenge is that the track between this part and the through hole via, the length of this track need to be exactly same as the length of the track on the top layer between this part and the through hole via. That may look very simple once you place a through hole via exactly into middle between these 2 parts. You will have exactly same distance between them. Yeah. Ta-da! Problem solved. It's not so simple. I show you. Do you know how many signals we need to connect this way? We need to connect 26 nets which are in this group. That means it's 1, 2, 3, 4, 5, 6, 7, 8. This is 8. Now, Control C, Control V. This is 16 through hole vias. This is 24 through hole vias. You see where I'm getting with this. We cannot connect, or we cannot place through hole vias exactly in the middle. We need to squash them somehow. This is not possible to do the layout this way. We'll do it like this. So we need 2 rows of through-hole vias. Problem is you then need to do length matching, because if they are not placed exactly into middle, it means this distance will be longer, on the other side it will be shorter. See, you need to do length matching here. I'm sure you can now fan out these signals. I'll show you how you can start and also explain what is important. I'll delete this and place the first through-hole via somewhere here. I know the through-hole via should be 1.3 millimeter from the path. Perfect. Now the second through-hole via. Shall I place it here? Here, here. How far we need to place this second through-hole via? You need to have space to route tracks between the through-hole vias. So the minimum distance where you can place it, you can calculate based on your minimum clearance, minimum track width. And in our case, it's 0.8. It's 0.9. I will move it here. What about this other row? Shall I place it here? 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 What is difference if I place the through-hole via here and if I place it here? You need to be careful and think about the power planes and ground planes. If you place through-hole via very close, there will be no space for copper to flow between the through-hole vias. If you have a look, this is plane, see? Here we can nicely see it flows between the through-hole vias. If you place them very close, you will have a big cut under the memory chip, big cut in ground, big cut in all the power planes. You don't want to have this. You really want to flow the copper between the through-hole vias. I will place it 1.3 millimeter from this path to 1.3. Now you can start routing them. You just have a look what is this signal. DRAM SDC key E0. And you will find it here. This one, what's this one? And I will connect it. Initially, just do it somehow. Also connect with the bottom. Yeah. Initially do it somehow, and we will do the length matching later. Before we move further, we will speak a little bit about DDR3 length matching. These are the rules which you need to use when you are doing layout for DDR3 memory interface. Be very careful, because these requirements, length matching requirements, are different between processors, and therefore always read design guide for the particular processor you use in your design. I open the IMX6 design guide and I will find the important table with the length matching rules. This is the table. DDR3 routing by byte group. As you can see, they split DDR3 interface into groups. For example, clock group with the clock signals in it. Address and command group with the address and couple of other signals in it. Byte groups, byte group 1, 2, 3, 4. Each byte has its own group. Each byte group contains 8 bits and DQM and DQS signals. You cannot swap or change these DQM DQS signals between the groups. This means the bits between 8 and 15, they have to use DQM1, DQS1. The bits between 16 and 23, they have to use DQM2, DQS2. It's important when you will be doing byte swapping. Remember this. And here is one more group, control signal group. On the right side, you can see the rules which you need to meet. For example, clock signal group cannot be routed longer than 2.25 inches. The signals within this group, they need to be routed within plus minus 5 mils. Address and command group cannot be longer than clock, cannot be shorter than clock minus 200 mils, and all the signals within this group, they need to be routed in plus minus 25 mils. Byte group, again, all the signals in this byte group, they cannot be longer than clock, and they must be routed in plus minus 25 mils. When you go on my blog, you can find there a document which I prepared for the presentation which I had in Silicon Valley. It's this document, and you can very nicely see the rules here. So this is the clock. Clock signals, they need to be length matched within plus minus 5 mils. Then here is the command address control signal group, which cannot be longer than the clock, cannot be shorter than clock minus 200 mils, and the signals itself, they should be routed in plus minus 25 mils. But whole group you can move here or here. Same for the data. Data itself, they need to be routed in plus minus 25 mils, yeah? But you can move all the group, you can move anywhere between the not defined or as short as possible to maximum clock. Why it is done this way? What do you think? Why we are routing these signals in groups? Because it makes the layout easier. For example, imagine if you have a long connector, SODIMM connector, for example, long one, and here is a processor. Then if you want to route signals which are in the middle, it's very short distance. If you want to route the signals which are on the edges of the connector, it's a longer signal. And if you have to length match all the signals to the same length, it would be very difficult to length match the signals which are in the middle. You would need to make them very long. This way, if they are split into groups, you can just route and length match one small part of the layout. It's very useful. So the first thing what we really want to have in our design is to see these groups. To create groups in OTU, it's very easy. And they don't call it groups, they call it net classes. Let's say we would like to create a clock group with these 4 signals in it. Go to Place, Directives, blanket and draw a blanket around net names which you would like to belong to this group. You can also draw a blanket around the port. Go to place, directives, this one, net class. Place it on the blanket, double click, and here you can name your group. You know how you would like to call it. We will use DRAM SD clock. OK, design update PCB. And I use these groups also for other interfaces and other peripherals because it's very useful. I will show you. You can very easily browse through your PCB. Execute changes, close. Click here on this PCB window, select nets, and here is the group which we have just created. Here are the 4 signals. When you click here, you see all the signals on your PCB here. This is, for example, a data group 0. You can see the signals which belong to this group, D0 to D7, DQM0, DQS0. And here are some other examples. UART, SD card. It's very useful. Once you create a group, you can very easily manipulate with the signals inside the group. For example, you can very easily assign a color to all the signals in the group. Let's say we would like to assign color to this data bank 0, right click, change net color. I really like green one. OK, now they are off. Right click, select them on. All at once. Why we are speaking about this? Because I will clear the selection and I recommend you to assign a color to each group. So when you will be doing the fan out here under the processor, in the processor area, you can very nicely see where the individual groups of the signals are located, on what pins. Before you start doing the memory fan out in the processor area here, be sure all the other paths, all the other signals, all the components in this area are in place. For example, all these ground paths, they have ground vias. It may not look important, but it can save you a lot of time. Trust me. Imagine, it's not difficult to place these vias and components here now. Yeah, you can place them very easily. It will need to be there anyway. If you don't place it now, what will probably happen, you will draw tracks in the area where these vias need to be placed. And you finish your DDR3 layout, and then when you start placing these vias, you need to move the tracks. You need to make space for these vias. And there will be a lot of tracks. You need to move a lot of tracks. And it's not necessary. When you place these vias, before you start doing the layout, you can just go around and that's it. No additional work later. I'm sure you understand. Hooray! Finally, let's do the fan out. But wait, where are we going to start? It doesn't matter, just let's do it. Oh, you can do it that way, or you can think ahead and plan the layout. Where would you start? Would you start from the processor edges or from the middle, from the paths located in the middle? From the middle. If you start doing layout from the processor edges, you start drawing the tracks and you go into the middle. Later you may find out there is not enough space to connect all the tracks in the middle, and you have to redraw everything what you have done. A lot of work. Trust me. I learned that the hard way. You don't have to. Start from the middle. Here, if you need space here, you have a lot of space here. You can draw tracks this way. How to decide if to use micro vias or through-hole vias? It's important because this is high-speed design interface. All the signals within group, same group, need to be routed same way. I keep repeating this rule. I read it a long time ago in an Intel design guide. I use it all the time and it helps. I've seen a memory which was not routed by this rule. Some of the tracks of one group were routed on top layer. Some of the tracks, same group, were routed in the middle of the PCB. This interface didn't work reliably. So ideally what you would like to achieve is, for example, this is address command control. You would like to start on top layer, go with all the signals, for example, on layer 2, then with all the signals on layer 3, split them on layer 10. See, all the signals. This is the group. All the signals in this group are routed same way. Then on the bottom and on the top. For the data, it's same. All the signals in this group. Layer 1 to layer 2, then on layer 3, back to layer 2, and on layer 1. And you remember, when we use micro vias, we will save a lot of space. So ideally we would like to use the micro vias in the group which has the highest number of signals. That's this address command and control group. That's why we will start doing this fan out with micro vias. Then what? Here is quite a lot of signals, and what probably very easily happen, we will need also some space in this area under these other signals, under these other paths. So on the layer 3, probably there will be no space. I will show you. I will select all the signals, all the memory signals, so you can nicely see it. Here are the micro vias for the address command control, and here is layer 3. Can you see? Here are the micro vias. And we need also some space here under these paths. So ideally we would like to go with all these paths which are here on different layer, not on layer 3, but on layer 10. See? And then we have also space here to route them, and here if we use micro wires also here. If you don't plan ahead, you may really have troubles to connect everything, or for example, you may go into a stage when you will have to delete a lot of work and try to do it again. Always try to plan and think about it. You will save a lot of time. To fan out the processor with micro wires, we will use the same technique as we used for the memory chips. I will draw a short track into middle between 4 paths, and I will copy, Ctrl C, and paste micro wire there. I will draw a short track on layer 2 and copy and paste micro wire here. By default, I always draw this L2 segment back under the path. It's only because I don't like placing micro wire under a path with different net. If needed, you can do that if it helps with layout. I always also draw this L2 track just short and straight. I don't use anything like this, or I don't do anything like this. Do you know why to keep it short? Because L2 layer is ground layer. If this connection is very long, you break the ground plane. It will not be as good as it can be if these connections are short. That's why I keep them short. Also, don't place the wires very close to each other. Again, there are some rules how close two holes can be drilled, so I just place it like this maybe. Why we don't use micro wire from layer 1 to layer 3? Why we are doing it so complicated that we go from layer 1 to layer 2 and then we draw this short track and go from layer 2 to layer 3? Because you can make micro wires from layer 1 directly to layer 3. You remember the ratio between hole and the length? If we use micro wires from layer 1 to layer 3, these micro wires would need to be bigger, and it would not really help us with layout in high density areas. That's why we use layer 1 to layer 2 and then layer 2 to layer 3 micro wires. If the pitch is bigger, you don't have to place the micro wire into middle. You can place it closer to a path. It's no problem. And then basically I will delete this. Once you have it, you just copy it and paste it. That's how I do fan out. Actually, many people ask me if I use automatic fan out. No, I don't use automatic fan out. I will show you. I don't know actually if you need to set something in Altium to create a really great fan out, but by default it will look like this. Outer out, fan out, component fan out. Okay. So no magic. That's the reason why I do it manually. Once you are done with the address, command, control, and clock groups, because you need to fan out also the clock groups between the first signals. They are really important. And they are located here. Then once you are done with this, continue with the data signals which are located close to this group, close to this address, command, control group. So continue with data groups here and data groups here. And you can see very nicely now how useful it is to apply colors to the data groups. You can very nicely see where individual pin belongs to which group. We will use through-hole bias for these paths, and we will start with differential pair because differential pairs need to be routed together. And on the beginning, you can actually decide how you are going to route them. If you first route these, you may not have space to route the differential signals properly. So start with differential pair signals. Before I actually click there, we need to set something because we have not been using differential pairs yet. We need to set up a rule which will specify how default differential pair will be routed. What will be the thickness of the track and what will be the gap between two differential pair tracks. Go to Design, Rules, Routing, Differential Pairs Routing, and here is the rule for the default differential pair. In case you have your stack up now, in case you know the exact track width and exact gap for specific impedances which you use on your board, you can specify the differential pairs now. But many times you don't have it yet. You don't know the exact parameters because you don't have the stack up yet. You may still be talking to your PCB manufacturer, for example, and but you still would like to do the layout, do something. That's why we are going to set up this default differential pair, and I will use my magic number, which is 0.1 millimeter for everything. Basically what we are doing is that we are going to occupy space with this default differential pair, which we will later just delete and redraw with a differential pair which will have the proper track width, proper gap for the specific impedance which needs to be used for that interface. This 0.1 number everywhere will actually occupy the space of 0.1 track, 0.1 gap, 0.1 track, that's 0.3 millimeters width. Sometimes this may not be enough. Sometimes you may want to occupy space of 0.4 millimeter. So sometimes you may want to put here 0.2, 0.2, 0.2, yeah. but for very high density designs this may be not very comfortable to do the layout. That's why I use it as 0.1. Press OK. To route a differential pair, just click here and click on the differential pair and you can start routing. As you can see, it will route both signals together based on the rule which we have just set up. So this track width, if I double click, it's 0.1 millimeter, and if I measure the distance between these tracks, distance between them is 0.1 millimeter. That's what we set up. Also, if you just hold cursor on a track, here on the bottom in the status bar, you will see what is the track width. See, 0.1 millimeter. I didn't place the through hole vias or the fan out close here to these two paths. And I have a reason for it, because for these DQS signals, I prefer them to take them out if possible. It gives me flexibility that I can choose where exactly I will go into the board, where exactly I will place the through hole vias. And the reason why I would like to have this flexibility is because I would like to route these two differential pairs from this group and from this group together between the data bits. I will show you why. One of the important high-speed design rules tell us that we need to keep big distance, big gap from the signals such clocks or differential pairs. You can see it here. See? Here are DQS signals, differential pair signals. Here are data signals, and there is a big gap between them. See? These data signals, they are routed much closer to each other. Here is also a big gap between this differential pair, DQS, and this data signal here. And we need to keep big gap between the differential pairs, or as big as we can. Now, why it is useful route these two differential pairs as neighbor signals, so basically together? Because we can save some space. How we are going to save space, I will show you. Maybe you already know, or you are guessing now. I will draw this signal between them as an example. I don't like this via pushing. Can you see how messy it can be? I will disable it. DXP, preferences, PCB editor, interactive routing. Do not allow via pushing. Okay. Don't forget, this is just an example. Okay. Now, count with me how many big gaps we will need. 1, 2, 3, 4. See? If I delete this, we need 1, 2, 3. That's how we will save space when these two differential pairs are routed together. And it's important in some cases when your layout is really packed, then saving space from this big gap can help you a lot. Now, this is important. Why do we do length matching? because we would like the signals from the group arrive together to the destination or in specified window. The thing is, because signal travels different speed on top and bottom layer comparing to the inside of the PCB, do not make this fan out too long on top or bottom layers, because this may influence the time when these signals will arrive. Try to make them as short as possible. Just continue and place through-hole vias for these two groups. Draw, draw, place through-hole via, or you can use copy and paste. No problem. And use micro vias for these other groups. Some people, some engineers, they place micro vias on paths. I don't do that. In past, we had problems with this kind of PCBs, with the PCBs which had the vias in path. We had problems during manufacturing, PCB manufacturing. We had problems during PCB assembly. That's one reason why I don't do it. Second reason why I don't do it, it will make your PCB more expensive. Third reason why I don't do it, there is no reason to do it. Why would you want to place micro via in path if you can place it here? Tell me why. There is no reason why. So if you really don't have to do it, don't place vias into path. If your design is not using micro vias, only through-hole vias, what you really may want to do is fan out these two rows of processor or BGA away from the BGA. So do it something like this. Go here and here, go here and here, and place the vias away from the processor, so you have some space here. Because it's very important how you place vias during BGA fan out, I'm going to show you two examples. First example is the simplest way of doing BGA fan out. It's this. Oh, I'm pretty sure you already seen this one. I'm so good in it. I'm so quick, so fast. Lay out this piece of cake. It's not so simple. Let's say we would like to fan out these first three columns of this BGA, and we would like to fan out these on one layer only, layer 3. One layer because we would like to use the other layers for something else. I will start doing the layout. First column is not a problem. Second column is not a problem. The problem is the third column, because it blocks via here. If I draw it a different way, this way, it's not a solution. It will block something else sooner or later. This way. This one is blocked now, here. What is even worse is that if vias are placed this way, not only this layer 3 is blocked, all the layers are blocked. In all the layers, you only can draw one track between these vias. And this is the main problem. That's the reason why we cannot fan out this third column, because between these vias we only can draw one track. What is the solution? Solution is make some space. Yeah, I will delete this. I will connect them on the top layer. And now we can draw them on layer 3. This is the second example, how you can do the fan out. See, we can fan out all these vias which are here. What would be even better if I move this via here? Why it would be better? I'll put it back. I'll show you. This is layer 10. See? Here this row again is blocking everything what would possibly need to go from here, from deeper from the BGA. It's blocking these signals. If we place it here, we open a space here. See? So I go here on the top and let's redraw it. We'll delete this. We'll delete this. And we will fan out the processor this way. Can you see the difference? And it's even more visible if you use micro vias. Always think about how you are placing the vias, because it's very important. Have a look on the layer 10. See, nice space here. If you have here some other tracks, other vias, you can very easily go out from the BGA. Now it's your turn. Go to the PCB and place the micro vias, place the through hole vias to fan out this processor area. When you finish the memory fan out, your PCB will look like this. Some tracks on the top, some tracks on the bottom, some micro vias, some through hole vias, nothing on layer 3, nothing on layer 10. We will use layer 3 and layer 10 to connect the processor with the memory chips. And we will start with address, command and control signals. So I click on the group, I go on layer 3 and I will start doing the layout. First I will highlight a net. I draw track, I place there buried via. This is buried via. It's not a through hole via. When I double click, it only goes from layer 3 to layer 10. And I copy and paste it. So I go on layer 10 and connect this. Go on layer 3, I highlight a different net. Yeah, this is exactly the way, how I would not do it. Why I don't do the layout this way, that I draw the full connections? What is this advantage of drawing connections from pin to pin? The thing is, it's very easy to route or start doing the layout when the board is empty, when you have a lot of space. Problem is to connect last 10% or last 5% of your PCB. And what can very easily happen, for example, in this particular case, let's say we have 26 nets, and you can very easily route 23 nets, but there may be problem to connect last 3 nets. There will not be way to connect them. You will have to delete a lot of your work which you have done. That's the reason why I don't route full connections. I do the layout partially, do some area, connect them together. I will show you. Go on layer 3, highlight, just very simply draw a track to the position where via need to be placed. Again, draw a track to the position where via need to be placed. If there is no space to fan out some of these signals, you can very simply just delete this simple track and redraw it. You don't have to delete a lot of your work. I learned this hard way. I remember one of the projects what I was working on when I was starting with layout. It was Saturday before Easter. I really remember it very, very well. And I was going to place the last via into the design, and there was no space to place one last via. It was horrible feeling, and I had to delete half of the PCB and redraw it again. I do remember it very well. It's real. It really happened. That's why I draw small parts of PCB and try to be sure I can go with everything out. Because if not, I can only delete small part and redraw it. I don't have to delete a lot of work. You understand that. Then go on layer 10, connect this. And place the vias. Again, always when I'm crossing tracks, when I'm changing layers, I don't draw full connection because it's much easier to place the vias later. You will just find the track. These tracks, 2 tracks need to be crossed. So I just go here, yeah, and place the via here. It's much easier than if you have to move these connections later once you draw them and you need to feed there some other tracks. You need to keep moving the vias and tracks. Just draw them this way, and place the vias on the end. In this particular case, because this is memory interface and it is balanced T-branch topology, you need to be also very careful where this via will be placed. Balanced topology will require that this length between this via and this via need to be same or very similar to the length between this via and this via. So ideally you would like to place these buried vias somewhere into middle, because if it's placed somewhere here, for example, you have to do a lot of length matching. You will need a lot of space to do the length matching here. Ideally, place them into middle. That's your next activity. Draw all these, and place the buried vias somewhere close to the middle. Now the data lines. When you will be doing layout for data lines, you really may want to consider bit or byte swapping. Why? Because memory interface is a high-speed design interface and you would like to make the layout as simple as possible. You are going to help me because you know everything important to do it. We would like to connect these 4 data groups from the processor to these 2 memory chips. One memory chip is on top, one memory chip is on the bottom. The thing is, 2 of our memory groups use the micro vias. So ideally we would like to connect these 2 groups to the top or bottom memory chip. To the top memory chip because we can do the layout on layer 3. Yes. And there are 2 memory groups which use through-hole vias, and ideally we would like to connect these memory groups to the bottom memory chip. Let's have a look. Don't forget, top layer is the red one, bottom layer is the blue one. So bank 0 is connected through micro vias from the top layer to the top layer. Perfect. We can do the connection on layer 3. Bank 1 is connected from top layer through the micro vias and it goes to the bottom layer. Not good. Bank 2, it goes from the top layer to the through-hole vias to the bottom layer. Good. And bank 3 goes from the top layer to the through-hole vias and it's connected to the top memory chip. Not good. We would like to swap this bank 3 and bank 1. Then everything would be perfect. We can have a look. It's bank 3, it is D24 to D31 and it's connected to U2. Bank 1 is from D8 to D15 and it's connected to U3. Let's go to the schematic and swap the byte. U2, U3. D8 to D15. I will move it away. We need to move also some other signals. What other signals we have to swap? DQS and DQM. We go here and we will move D24, D31 here. We will move DQS here and we need to move also DQM here. Okay, and we can move this here. Here and here. Be very careful when you are swapping bytes. You need to also watch to what clock the memory chip is connected and what clock enable the memory chips are connected. How do I know this goes here and not here? Because this is upper byte, lower byte. Upper byte is DQ8 to DQ15, yeah? So all the bits which are connected here need to have the strobe signal here. Same here. Lower byte, upper byte. Okay, we can synchronize the PCB with the schematic. And let's check the changes. Bank 0, top microvias top. Bank 1, top microvias top memory chip. Perfect. Bank 2, top through-hole vias bottom. Perfect. Bank 3, top through-hole vias bottom. Perfect. This is why we do the byte swapping. We are going to do layout for these two groups. Now, think a little bit. Maybe it would be easier if these two banks are swapped. So we can connect this here and this here. So we would like to swap D0 to D7 with the bank D8, D15. Let's do it. Remember, here is yellow, here is blue. We are going to swap it blue, yellow. What I'm going to do? I will move this away. I will put this up. I will put this back. We need to swap also. You can do this by yourself now. You know everything. Here. And we need to swap one more thing. This. Update the PCB and we are done with the byte swapping. See? Blue, blue, yellow, yellow. Perfect. Let's connect the data signals together. Again, we are going to do some pin swapping, and this time it's called bit swapping. There are some rules how you can swap the pins within 1 byte. Open the Freescale design guide and here you can read. We cannot swap DQS and DQM signals, and we cannot swap the lowest order bit within byte line because it must remain on the lowest order bit. We can swap the other bits. Basically, this means we can swap the bits, the 1, 2, 3, 4, 5, 6, and 7 between them any way we want. I go on layer 3 and we will start the layout with the signals which cannot be swapped. So DQS, for example. And I will use dim. Do you know what's different between mask and dim? If you use mask, you cannot work with these other signals. If you use dim, you can work with these other things. See? So for the layout, I will use the dim mode. I go here and at this stage, it's not important how exactly you draw the lines, just connect it somehow. DQM is the second one which we cannot swap, so I will just connect it, and DQ0. I will just connect it. Okay, here we have 3 unconnected pins, so we need to connect 3 pins here. Ideally, because this interface needs to be length match, ideally we would like to connect this pin which is here with something what is far away. Pin which is here with something what is far away. We don't want to connect this pin with this pin, because then we have to do a lot of length matching. So for example, let's say we would like to connect this one with this one. At this stage it's not possible to connect them together because these are different bits, but we will swap them. I only route them together, close together. Then this one. And you can see I'm using a special mode during this routing which can push tracks. Can you see that? Here down in the status bar you can read what mode I'm using. It's called push obstacles. Press Shift R, you can change the mode. Hack and push. Stop at first. Auto route, auto route. Ignore. Ignore is I can go through. See? I use ignore and I use this one, walk around. Usually I use walk around obstacles by the end of the design. At this stage, this push obstacles is the best option. Okay. Just route them close to each other. Okay. This one is very far away, so we would like to ideally connect it somewhere here. This one somewhere here. This one here, and this one I don't want to go with him around, so I will reroute this one this way so I can connect it easy way like this. Good. Let's swap the pins. If you cannot read the net name and you would like to know, for example, now you cannot read the net name, you would like to see what is this net, just hold the cursor, again read down in the status bar. See DRAM D7, or you can zoom in. We would like to swap D7 with D2. I go to the schematic and I will D7, D2, design update. You can swap all the signals at once. I will only show you one example. You know how to do it. D7, D7, now we can connect it together. And this is your next activity. Finish this byte. Do the layout for rest of the data groups. At this stage, do not really care about how the signals look. Try to do I will show you. Try to route the differential pairs as neighbors, and do not mix the signals between the groups, because ideally you would like to also keep bigger gap between the signals which are from different groups. See, here is a bigger gap between this blue data group and this yellow data group. So it's your next task to do. And I magically connected these bits together. I know I asked you to connect the signals together, but I would like to speak about this total length of signals, so I had to do it also by myself. Before you start looking into total length, be sure you also connect this yellow group. Because even I have routed this blue group, it doesn't mean it's routed correctly. Because when you will be doing layout for this yellow group, you may find some potential problems. And I already see one. Can you see it too? I will give you a clue. Can you see it now? We learned that ideally we would like to route these differential pairs together as neighbors. And when you have a look here, this D0 signal is in the way of this differential pair. So we need to somehow reroute this D0 this way maybe. And you may want to change these bias here, or you may want to swap some of these pins. I'm sure you will figure out a way to connect it. Once you connect this yellow group and this blue group, click here on one of the banks and order the signals, the tracks by length. Click on the longest one and have a look. Can you make it shorter? Not really. So this is going to be our target length. Click on the shortest signal. Can you make it longer? Yeah, no problem. I can do it longer because I don't have the yellow group routed. For you it will be more difficult. Then click on the shortest one again and make it longer again. I call this preliminary length matching. At this stage we only would like to occupy space. We would like to see that we will be able to achieve the target length. We would like to see there is enough space to add all the waves, you know, by the end of the design. Because you don't want to find out by the end of the design that, oops, I cannot length match DDR3 interface because there is not enough space. I'm sure you can do this by yourself. I only finished this. And this one, I would like to show you this one because this is a special track. It goes around hall. Do not route tracks very close to hall. You need to keep at least 0.2 millimeters distance from hall. Otherwise, they in the the PCB manufacturing company, they will tell you that they cannot manufacture the PCB. They will ask you to move the track away from the hall anyway. And for the high-speed designs, you really don't want to route very close to hall because the environment change where the hall is located, and it may influence the signal which is routed very close to the hall. So don't route the signals very close to them. You can finish it. You don't have to length match them very precisely. What I normally do, I length match them like in 1 centimeter, and ideally you would like to make them a little bit longer than the longest required signal it is, when longer than the target signal is, because to make signals shorter is always easier than to make them longer. So when you finish, when you connect all the data signals, in the next step your task will be to preliminary length match these. To make it clear, at this stage only do the preliminary length matching of the data signal, these and these. Why data signals only? Because it is quite easy to do, it is fast to do, and at this stage when nothing else is routed, only the memory design, it is very useful to know that, for example, the memory chips are in the right position, that you will be able to connect all the bits, and it's also very useful to see that you will have enough space to do the length matching. Do not do any length matching for the address command and control signals. We will do preliminary length matching of these signals a little bit later, because it is not so easy. It is a little bit more difficult, and it is not needed at this stage. Only what we would like to see now is the area where, or the area which is needed for the DDR3 layout, to see the something what I call envelope around the DDR3 area, this. So you know where you can route the other signals. You see the space where you can go. Several tips before we finish this lesson. Sometimes you may work in an area with a big component, and when you want to click on a track or on a via in this area, the big component keeps selecting. All the time it keeps selecting. You can disable it very easily. Just double click on the component, lock it down, press OK. Now when you click in the area, never select again. It's very useful. About these short tracks on layer 2. When we were speaking about these microvias before, I always placed in the examples I showed you this microvia exactly under a path. It is not required to place this microvia under a path. Important is to keep this track short, so the ground on layer 2 is as good as possible. About fan-outs for differential pairs. We were speaking about this. I didn't show you example. I'm going to show you example now. I wouldn't fan out differential pairs this way. Here are the differential pairs. I would do it this way. Okay? And when we are speaking about differential pairs, usually you route differential pairs through this button. So both signals are routed together. Sometimes you may want to route one signal first and then the second signal. I'll show you. This way. And now the second signal. It's very useful when you switch the proper routing mode for this. You remember, watch here in the status bar and press Shift R. You can switch between the modes. So I will be doing Shift R, and walk around obstacles is the routing mode. Then just go around the first track. It will automatically keep the proper gap, and it will automatically use the proper track width as it is defined, specified in the differential pair rule. When you are routing reset for DDR3 interface, keep bigger gap, bigger distance between the DDR3 reset signal and the other DDR3 signals. You can see it here, bigger gap on layer 10, bigger gap, yeah? And that's everything for this lesson. Please always read design guide before you start doing the layout. Read design guide when you are working on particular interface. For example, here you can see there is a lot of pages about DDR3 routing rules, DDR3 placement, and about all DDR3 interface. There are differences between chips. That's why it is important always read the design guide for particular chip. Don't forget to work on the activities for this week. Do the placement and fan out under processor. Do the fan out for the memory chips. This is simple. Everyone can do this. Do the fan out for the DDR3 interface under processor. Connect processor and memory chips together. Do the preliminary length matching of the data signals. It will really help you. Next time, when you will be working on your next project, you will feel more confident. You are doing it for yourself. Next week, we are going to finish the fan out, and we will be speaking about some high-speed interfaces. So I'm looking forward, and see you next week.